Our goal in analyzing this data set is to generalize the results to the population that the sample was drawn from. In other words, if we see changes in functional connectivity in our sample, can we say that these changes would likely be seen in the population as well? To test this, we will run a group level or second level analysis. We calculate the mean and standard error for a correlation estimate, and then test whether the mean is statistically significant. In the last video, we analyzed a single run for a single subject. In other words, we ran a first level analysis. This is great for seeing whether there are significant correlations within a single subject, but we cannot do any group inference. To load more subjects, we will first have to download more subjects. Go back to the arithmetic study on the OpenER website and download the functional and anatomical data for subjects 2 through 6. This will take a while, so I'm going to speed it up, but after you just do a couple, you should be able to get the basic pattern down. If your downloads folder is the default, you can move all of the downloaded images to their respective folders by navigating to the arithmetic directory and copying and pasting this code, which you can find in the information box down below. Then from the Conn GUI, click on the Setup tab and click Basic. Change the number of subjects from 1 to 6 and observe how the number of sessions and the repetition time expands to reflect the total number of subjects. Each number corresponds to each subject in the dataset. For example, the third number in repetition time corresponds to the third subject that we load. If the third subject's TR was 2.5, for example, we could make an edit like this. In reality, each subject's TR was 3.56, so I'll change it back. We will then load each subject's anatomical and functional data. The easiest way to do this is to use the Find filter beneath the Image Extensions field. In other words, right here. For the structural images, type T1W, since every anatomical image in this dataset contains that string, and then click Find. The current directory and its subdirectories will be searched for any images that contain the string. Notice that I've already analyzed sub01 in an earlier video, so I have many different files that all contain sub01t1w.nii. What I need to do is find the original, which is right here, and then I can hold Control to select the other images for the other subjects. Now also hold Shift and select all the images, and then click Import. You should see something like the following. As before, scroll through the slices of each subject's anatomical data to make sure that nothing looks like an anomaly. Now do the same procedure for the functional images. Click on the Functional tab and use the Find filter to look for any images in your directories that contain the string bold. Again, sub1 has already been processed, so we have a lot of files. The original one should be right about here. And then we select everybody else as well. Make sure to highlight all of the subjects over here by shift and clicking, and then click Import. After a few moments, you should see a pop-up window that says 6 files assigned to 6 subjects. Again, take the time to look at each subject to make sure that there are no anomalies. Now this guy has gigantic ventricles. Is that going to be a problem? We don't know for sure yet. We can still probably segment the gray matter without any problems, but I would definitely keep an eye on this and see whether any of the estimates turn out to be outliers, because the ventricles may have some kind of indirect effect on that. Now click the pre-processing button to begin pre-processing all the subjects in a single batch. This will take about 5 to 6 minutes per subject, or about 30 minutes total. We're going to fade out now and come back when it has finished. When it has finished, check the ROIs and covariates first level tabs, this time scrolling through each subject. Subject 2, for example, if we look at the scrubbing field, has 1, 2, 3, 4, 5, 6, 7, 8 volumes that have been marked as outliers. Each of these marked volumes will be inserted as a regressor into that subject's first level design matrix. This is also called scrubbing, which removes their variance from the rest of the time series. I'm not going to go through all the subjects here, but just like we did with the first level analysis, you should check each one to make sure that everything was segmented appropriately. Now click on Done to begin denoising. This will take a few minutes per subject, and again, we're going to fade out here and come back when it's finished. When denoising has finished, click on the Denoising First Level tab to review the effect of accounting for different confound regressors. The layout is the same, the only difference is that now you can click through all of the subjects. Review them using the same criteria that we did in the denoising video, and then click the Done button to proceed with the first level modeling. When it's done, the preview window of the tab Analysis First Level will be the same as for the individual subject analysis, but now with all of the subjects listed. Click through them all to review their connectivity maps after denoising has been performed. If you are satisfied with the quality checks, click on Done to begin the second level analysis. Make sure that all subjects and all conditions are checked, and then click Start. This will only take a few minutes. When you have finished the group analysis, you will have access to the last tab, Results Second Level, which looks something like this. This will display a whole brain map of the correlation for the contrasts that you specified in the Setup tab. You may wonder what contrasts exactly we did specify. The default that has already been created for you is a condition called REST, which is a correlation map generated for each subject in each ROI. You can see this in the Setup tab under Covariates Second Level. These are then averaged over all of the subjects by using a contrast vector in the Covariates tab of the Setup screen. You will see a list of covariates that will be entered into the second level model. The covariate all subjects has a contrast vector 111,111, representing an average taken over all 6 of the subjects. Click back and forth between the Setup and Results Second Level tab to see the correspondence between how the experiment is set up and the results that are generated. What if we wanted to create another contrast? For example, compare the first 3 and the last 3 subjects, as though they were different groups. We first need to create 2 separate contrast vectors, one for the first 3 subjects and one for the last 3. From the Setup tab, click on Covariates Second Level, and hover your mouse over the bottom left corner of the Covariates menu. Click on the plus sign and label the covariate Group A. In the Values field, enter the following values, 111000, and do the same for another covariate called Group B, entering this vector, 000111. Observe how the red dots change according to which contrast vector you have selected. The dots will be positive for the first 3 subjects for Group A and positive for the last 3 subjects of Group B. Now when you click on the Results Second Level tab, there will be 2 new subject effects, Group A and Group B. Highlighting either group separately will show the results for that group. To take a contrast between the 2, on the other hand, we will hold Shift and click to highlight both groups and enter a between subjects contrast of 1, -1. You can also click on this menu to automatically do it for you. For example, if we wanted to know where Group A was greater than Group B, or vice versa. If you want to account for other sources of subject level variance, such as age or sex, these can also be entered into the covariates second level tab. Create a new contrast, for example, age, and enter the values for each subject. For example, let's say that the first subject was 18, the second subject was 21, the third was 24, 26, 17, 19. I'm making these up, but you should have access to these if you ran the experiment yourself. If you want to mean center any of these covariates, such as age, click on the Covariate Tools menu and select Orthogonalize Selected Covariates and highlight the All Subjects covariate. This will mean center all of the age values relative to the total number of subjects that we have. You can then go to the Results second level tab, click on age, and this map will show you where there are significant correlations with that. The resulting correlations will show where there's a significant correlation, again, between the correlation effects and a covariate such as age. For example, does the correlation within a voxel such as this one significantly show an association with increasing age? Now that we have carried out our second level contrasts, we will go on to interpret the results. OnToolbox will generate many different graphs automatically, one for each of the ROIs you specified in the Setup tab, which are populated here. These connectivity maps depict the correlation between each ROI and the rest of the brain in the Seed to Voxel Maps tab, as well as the correlation between each ROI with every other ROI in the brain, which can be found in the ROI to ROI tab. For the condition and C that you highlight, a corresponding second level map will be displayed on the right side of the Conn window. The results are, by default, displayed on axial slices at an uncorrected p-value of 0.001, which you can change if you want. And the color bar to the left represents the strength of the t-statistic. Hovering the mouse over the voxels displays the t-statistic and p-value for the contrast highlighted in the subject effects window, and clicking on a voxel generates a bar plot showing the strength of the contrast estimate. The results preview panel includes more options for viewing the results. Clicking on the Plot Subjects button, for example, gives you the option of displaying the results for each subject in a montage. Note how the group level result represents the strength of the overlap between the individual subject maps. You may have wondered why the right window pane says Results Preview when it appears that we have generated our group level results. The map has not actually been written to the disk yet. We will do that by clicking on the Results Explorer button here. I've already done it, so I'm going to load existing analysis results. After a few moments, another window opens up, giving you more options for viewing the results in different orientations, for example, on different surfaces. The window can be divided into three parts. 1, the threshold panel up here, 2, the display panel over here, and 3, the coordinates panel down here. The threshold panel allows you to set a threshold if you choose the advanced family-wise error control settings. These other defaults will work fine for most purposes, but if you want to see what goes on under the hood, you can select this Customize option here. For example, voxel-wise threshold specifies the cluster forming threshold, or how significant a voxel needs to be considered part of a cluster. The field below it, cluster threshold, sets the threshold of which clusters will be displayed. In other words, this is your alpha threshold. The menus next to the voxel threshold and cluster threshold fields specify which kind of correction mechanism to use. For example, switching from p uncorrected to ftx stat allows you to specify a t-statistic instead of a p threshold. Likewise, the cluster threshold can be changed from an FDR threshold to FWE or even uncorrected. The last pair of menus specify whether the tests are one-sided or two-sided, and whether to use parametric or non-parametric methods for correction. If you want to use a correction method that does not depend on parametric assumptions, such as normality, change parametric stats to non-parametric stats. This will prompt you to select a number of simulations, and in general, around 5,000 simulations is recommended. The display panel shows the results by default on a glass brain. The buttons on the right side of the panel allow you to visualize the results in different ways. For example, the button in the upper left part of the panel will display the results on an inflated brain, almost as though it's on a surface. Whereas the button here will display it on a typical cortical map. The other buttons are relatively straightforward to use, such as displaying the results on individual slices. The last button we will discuss here is the button that says SPM. This will load the results into the SPM contrast manager, which can then be thresholded and viewed using the SPM interface. For more details on how to do this, see the link down below. The bottom panel shows the coordinates for each cluster that passes the thresholds specified above. Clicking on each set of coordinates will highlight a cluster by slightly darkening it. These coordinates can then be reported in a table as significant results, given your thresholds. Close the Results Explorer window, and then click on the ROI to ROI tab. This also displays functional connectivity results, but at a different resolution. Instead of a whole brain connectivity map, we only see ROIs that are significantly correlated with other ROIs. The options for selecting different contrasts are the same as for the seed to voxel results. The red lines indicate which ROIs are significantly correlated with the selected seed, and blue lines indicate significantly negative correlations. More or fewer axial slices can be displayed by clicking on the up and down arrows here. Clicking on each of the nodes in the results pane will display a bar chart showing the size of the effect for that ROI to ROI correlation, and clicking on the Display 3D button will show a transparent brain with all of the nodes overlaid on it. The ROI to ROI results allows you to see in more detail how nodes of certain networks are correlated with other nodes in the brain. Scroll down to Seeds, Sources menu, and then Network, Salience, ACC, and click on it. This uses a node within the anterior cingulate cortex as a seed and correlates it with all of the other ROIs in the brain. Now click on the Results Explorer button to open a new results window. This will display the significant connections or correlations between the nodes as a connectome ring. The salience.acc node in the lower right hand corner over here, for example, is connected through curved lines to other nodes. If you want, you can restrict the number of nodes you are testing by going to the menu Analysis of these number of connections among 164 ROIs. And then, for example, simply highlight a subset of nodes. The connectome ring will then update, only showing those nodes that you selected. Each time you press the Results Explorer button, results were generated and output in the directory structure that Conn automatically created as part of your project. If you go back to your MATLAB terminal, for example, you will find that you have been moved to a folder called Conn Arithmetic Project Results Second Level SBC01 All Subjects Rest FP frontal pole _R. This contains the results you were just looking at in the GUI. If you type ls, you should see the following. These are the images loaded by the Conn GUI when you look at the results. The file spmt0001, for example, shows the correlation to t-statistic map that was created for the node you selected. You can open it up in any other software package, such as AFNI or FSL. The beta maps are Fisher Z-transformed images that can be used with any other software package, such as AFNI or SPM. After you've run your first and second level analysis, you will also have a directory called Results First Level. Let's navigate to that folder. If we go into SBC 01, just like in the second level directory, you will see a list of beta images, one for each source or ROI that you specified for each subject. And these are Fisher R to Z transformed images that you can use in another program such as SPM or AFNI or FSL if you want to run a group level analysis in those toolboxes. You will also find that it contains several .mat files, one per subject, which in turn contain a connectivity matrix for each ROI to ROI Fisher transformed z-value. You can load this by typing in MATLAB, for example, load results ROI subject 01 condition 01. After doing that, you will see a variable called z in your workspace. If you type z, this is a connectivity matrix for every pair of ROIs that you specified in the Setup tab. You can find out which column corresponds to which ROI by typing names and pressing enter. You can then extract the connectivity values for each pair of ROIs you're interested in. For example, let's say this one. Enter these values into a statistical software program such as SPSS or R and perform an analysis on them. That's it for viewing the results. We now move on from resting state data to task-related data using a process called psychophysiological interactions. All that and more in the next video.